A new high-performance field reversed configuration operating resume in the C2 device. Number 1. Introduction. The field reversed configuration (FRC) is a prolate compact toroid formed with poloidal magnetic fields. The FRC continues to be explored experimentally and theoretically because it offers a high potential for a fusion reactor, including very high beta, simple geometry, neutral diverter, and ease of translation. The FRC could lead to an economic fusion reactor with high fusion power density, possibly using aneutronic fuels such as D, helium, and proton beryllium. Large FRCs are produced in the C2 device by combining dynamic formation and merging processes. Two compact toroids formed T equals 0 by a variant of the field reversed theta pinch method are translated supersonically into a central stainless steel confinement vessel where they collide. T to 30 microseconds and progressively merge into a long-lived to 1 millisecond FRC. An FRC equilibrium in the C2 device is shown in Figure 1 as calculated from the Rami-Rich code field line contours are traced and plasma densities are indicated with colors. Typical C2 equilibrium FRC parameters are T equals 0.3 millisecond separatrix radius, R to 0.4 meter separatrix length, L to 3 meter external magnetic field, B to 1 kilo Gauss average density, N to 4 cross 10 to the 19 power meter cube. Deuterium temperature T to 0.5 kilo electron volt and electron temperature T to 0.2 kilo electron volt. The FRC lifetimes are to 1 millisecond. During the decay, the FRC separatrix shrinks radially and axially, and the plasma temperatures gradually decrease. The main goal of the C2 experiment is to demonstrate FRC sustainment with neutral beam NB injection for heating and current drive and with pellet injection for particle refueling. The C2 20 kV hydrogen NBs are injected tangentially to the FRC current direction CO injection with an impact parameter of 0.2 meter. The FRC parameters listed above are stable for NB capture. Monte Carlo simulation indicate that seen through and fast orbit losses less than 10% and for fast ion confinement slowing down time. FRC lifetime. The 20 keV fast ion have Betatron orbits with large exclusions outside the FRC separatrix. Typical outer turning radii are 0.55 meter. The confinement properties of the C2 FRCs are good, comparable, or exceeding these of past FRCs. However, further improvement in the FRC confinement is desirable. The global power losses are about 10 megawatt midway T to 0.5 millisecond through the FRC lifetime, hence they exceed substantially the available NB input power to the FRC. Accordingly, present C2 research seek new way to improve FRC confinement, while attempting to build up a significant fast ion population. Rotational stability also remains a concern for C2 FRCs, as will be detailed in SEC 2. During the first year, new experimental techniques have substantially improved the confinement and stability of C2 FRCs. A plasma gun introduced at one end of the C2 device is key, together with NB injection, to obtain much improved FRC data. This paper reports on these new results, referred to as the high-performance FRC operating regime. The present paper is organized as follows. Section 2 details FRC rotational stability, and how it can impact NB fast ion confinement. Section 3 describes the C2 and plasma gun and its main beneficiary attributes. An attempt is made to dissect the new HPE operating regime in SEC 4. One component at a time. The data are discussed in section 3 and the results are summarized in section 5. Section 4. Thank you.